we're live. All right. So which ones would we like to see gone over for the review? Which one? So we are on page number chapter 1 review. Anybody got the page number? 118. 118. All right, which ones would you like to see gone over? If none, then you just we can start working, and then as you have questions, we can do that too. Whatever you want to do. 25. All right. So let's do number 25. 25. It says, what's the limit as x approaches 1 of e to the x minus 1 times the sine of pi over 2 x. What's the first step? What do we always try first? Direct substitution. So let's try it. If we get 1 right here, so that would be e to the 1 minus 1 times the sine of pi over 2 times 1. Well, what is e to the power of 0? 1. And what's the sine of pi over 2? Sine of pi over 2 is 1 multiplied together. So when it comes to pi over 2, remembering how to do that, when it comes to the quadrantal angles, the angles that are on a quadrant, I like to use the unit circle. And so this is pi over 2, and the point from the unit circle is 0, 1, and remembering that the sine is the y value. So the sine of pi over 2 is 1. So 1 times 1 is 1. So yay, it worked. You don't have to do any crazy algebra. Yeah. 29. 29. Says, find the limit as x approaches c of f of x times g of x. Okay, a couple different ways you could do this, and in fact, let's get all the information here. We know that the limit as the limit of f of x as x approaches c is equal to -3, and then the limit as x approaches c of g of x is equal to 1/2. Okay, and actually with this information, there's only one way to do this. You need to realize that we're going to use our limit rule. Yeah. Yeah, the answer is -3. There we go. Because -6 times 1/2 is -3. Yeah. When it comes to these, you're going to take the limit of this guy and multiply it by the limit of this guy. So it's -6 times 1/2. Okay. Others. 35. 35 is the limit as x approaches 0, and I'm saying that wrong. It should be the limit of 20 times the quantity of e to the x over 2 minus 1 over x minus 1 as x approaches 0. So, would direct substitution work? Would. So, I'm just going to say direct substitution for that guy. And that should give you something, well, I plug 0 in here, that's going to be e to the power of 0, which is 1. 1 minus 1 is 0, so 0 times 20 is 0, over 0 minus 1, which is negative 1, so 0 over negative 1 would just be 0. So direct substitution works. Plug in the numbers and you should get an answer of 0 when you do all that math.
Then, like, with that,
Mm-hmm.
because this is a graph, usually the graph the function that's making it, so we would have like a very popular like, I would not want to graph that by hand.
This one you should be able to find without a calculator. You wouldn't have to graph it per se.
But just like in the directions it says
Right.
to graph it.
Right.
For that, then,
Yep. If I tell you to use a graphing utility, then I'll let you.
okay.
Yeah. Yep. And then say use a table to reinforce your conclusion. Everybody know how to make tables for limits? All right. I won't do that on this problem then, because you know how to do it. So. Other ones, unless you want to see it, then I'll do it. All right. Sure.
I just have a general question.
Yeah.
So, on the ones where it's like, as x approaches infinity, and then, there's like a denominator, you can consider the rational function, and then if it does not exist, and there's a horizontal asymptote, it does not exist, and you say like it goes to infinity, is it also infinity if it says like as x approaches negative infinity, or you have to
You have to analyze it.
Okay.
Yeah. Like, for instance, is 85 one of your homework problems?
Yes.
85? Let's look at 85. 85 does something like that. The limit as x approaches negative infinity of the function 3x squared over x plus 5. Okay. So, let's analyze the, first off, if we were to do direct substitution, it would fail because it's indeterminate form. So, after that, we need to look at the degrees. The degree of the numerator is bigger than the degree of the denominator, right? What does that tell us? Okay. So what does that mean about the limit? Does not exist, right? It's either going to be, so it does not exist, but we need to be a little bit more specific than that in this case. We need to say, is it going to increase without bound, or is it going to decrease without bound? Another way to write that, is it going to be positive infinity or negative infinity? So, doing this analytically, we're going to divide by the highest degree in the denominator. So we're going to divide by x. So this would become 3x squared over x over x plus 5 over x. And that would be the limit as x approaches negative infinity. So then this guy in the numerator becomes 3x, and the denominator becomes 1 plus 5 over x. Now we can evaluate it with negative infinity. So if we were to put negative infinity into the x up here, we would get 3 times a negative big number. So really small number because it's negative, right? So this would be, in the numerator, become negative infinity. And the denominator would be 1 plus, this would be 5 over something that's really big. So what did we say that is? 0. So it's 1 plus 0. So this is negative infinity over 1, which is negative infinity. Okay? So the limit does not exist. That's right. But more specifically, it doesn't exist because it decreases without bound. Okay. And it approaches, it goes to negative infinity. Cool. Yeah.
Can we do 37 including?
Yeah, let's do it. Absolutely. This is a good one. So we have that s of t, this is 37, s of t is equal to negative 4.9 t squared plus 250. And that's the height of an object that has fallen for t seconds from a height of 250 meters. The velocity at t equals a, so we have that t equals a, and we know that the velocity is equal to the limit as t approaches a of s of a minus s of t all over a minus t. Alright, so when we plug this in, let's do s of a first. And for 37 it says that t is equal to 4. Okay, so that's 4 seconds after it started falling. So t is equal to 4. Thus, a is also 4. So, let's plug in s of a. We get negative 4.9. And instead of t, I'm going to do this problem the entire way. So I'm not going to skip any steps. Okay. So right now it's going to be 4.9 instead of t squared. It's going to be a squared. I'm not going to substitute 4 in yet. You could skip this step if you wanted to. So negative 4.9 a squared plus 250 minus the quantity of negative 4.9 t squared plus 250 all over a minus t. That's the limit as t approaches a. Now we're going to plug in 4 for a. So wherever there's an a in this equation, we're going to plug 4 in. So that makes it the limit as t approaches 4, because a is 4, of negative 4.9 times 4 squared plus 250. And then over here, I'm going to distribute that negative, so it becomes plus 4.9 t squared plus 250. Excuse me, it should be a minus 250 because negative times a positive. All over a is 4, so 4 minus t. Now let's do some math. 4 squared is 16 times negative 4.9. So negative 4.9 times 4 squared is negative 7.84. Oh, hold on, I gotta get a scientific notation here. Let's do that. Okay, so negative 78.4. So this is negative 78.4, and then let's add 250 to it. And that's 171.6. So this is 171.6. Oh, you know what? Actually, we could even just skip that, and let's cancel those out. The positive 250 and the negative 250. So then the other answer is the one we're going to want is negative 78.4. So it's negative 78.4 plus 4.9 t squared all over 4 minus t, and that's the limit as t approaches 4. Alright, now we need to do some algebra to get t out of the denominator, because if we leave t in the denominator, then direct substitution fails. We get a 0 in the denominator. So let's take this numerator and we're going to factor out 4.9. So, and I'm going to move the t squared out front. So we get 4.9, and then it's going to be t squared minus, let's take 78.4 and divided by 4.9. So 78.4 divided by 4.9. And we get 16. So it's t squared minus 16 divided by, what did we do before to get this to reorder it? How does that work?
That's then -1.
Yep, so negative t minus 4. And that's the limit as t approaches 4. Again, the technical rules are for limits is you're not supposed to stop writing this limit notation until you do direct substitution. So when you actually substitute this 4 in, that's when you can stop writing this limit notation. On the AP exam, they kill you for that. So anyway, how does this factor? Yep. So let's write that up here. This is t plus 4, t minus 4. So what can we cancel? Yep. And so we divide out the t minus 4's there. And we are left with the limit as t approaches 4 of 4.9 times the quantity of t plus 4, but we need to tag this negative on, so it's negative in front there. Cool, no more denominator, now we can evaluate it. So plug in 4 for this, so we get 4 plus 4 is 8, and then so now we can stop writing the limit notation, and we can say negative 4.9 times 4 plus 4, and that's 8 times 4.9, so negative 4.9 times 8 gives you negative 39.2. And the velocity would be meters per second. Meters per second. Okay. Was 38 part of the homework? Okay. So if you were to do something like 38, you would first have to set the original equation equal to 0, and then whatever you get for that, that would be your value for t, for time. That's how long it takes to get to 0, and then you do the same step, same process that we did before. Okay. Other ones. Back row. Back row. Yeah, Morgan? 21. Absolutely. Yeah. The limit of, I'm going to rewrite it like this, 1 over x plus 1 minus 1 over x as x approaches 0. Everybody would agree that direct substitution fails? So, what did we do to combine these two fractions in the numerator? Yeah, so I multiplied, we want to get common denominators. So this is currently a 1. So let's multiply this fraction by x plus 1 over x plus 1. So then the new numerator becomes, I'll write it down here, the limit as x approaches 0 of this numerator becomes 1 right here, and then minus the quantity of this, x plus 1. And then the denominator is x plus 1. And that's all over x. And I'm going to write x over 1. Okay. The numerator can be rewritten as, well, the 1's will cancel out because it's 1 minus x minus 1. So the 1's will cancel out and we're left with negative x. So this is equal to the limit as x approaches 0 of negative x over x plus 1 over x over 1. And then I'm gonna flip the denominator, bring it up and cancel, and multiply. So 1 over x. And so now that goes away. And these x's will divide out. So that is going to equal the limit as x approaches 0 of negative 1 over x plus 1. And at this point, direct substitution works. So we plug in 0, we get negative 1 over 0 plus 1 is equal to negative 1. Cool. Yep, those ones are tricky. Other ones. Other ones. Now is the time to ask. Cool, 45. I think I'm going to $45. Here we go. The limit of f of x as x approaches 2, where f of x equals, and here we have a piecewise function, x minus 2 quantity squared, for x is less than or equal to 2, and 2 minus x, and I'm going to rewrite it as negative x plus 2 because that puts it in y equals mx plus b form, and I'm just used to that but more, so it helps me graph it easier. X is greater than 0. So the limit as x approaches 2. So the directions say find the limit if it exists. If it does not exist, explain why. So, oh yeah, not. I probably looked at something. Yeah, they're both 2. Sorry. All right. So, okay. So if the limit exists, that means the right-sided limit and the left-sided limits are going to match, right? So let's take the limit as x approaches 2 from the left, and we'll do the limit as x approaches 2 from the right. And if we get the same value, then it exists, and it would in fact be that number that we get. Okay. This is doing it analytically. If you wanted to graph these, you could do that as well. Graphing is, I'm more visual, so I like making a graph and kind of figuring out. So you could graph these and then just look at it and get it. But this is analytical explanation here. So the limit as x approaches 2 from the left. Well, 2 from the left would be using this portion, the top portion of the graph. So we're going to use x minus 2 quantity squared. So we can do direct substitution because it works. So we plug 2 in, and we get 2 minus 2 squared, and that's 0. Okay, so that's the limit as x approaches 2 from the left. Now let's try the limit as x approaches 2 from the right. And for that, we're going to use the bottom portion of the function because greater than 2 would be from the right. So we're going to use of negative x plus 2. And again, direct substitution would work. So let's plug in 2. So we'll get negative 2 plus 2. And that also equals 0. So because the two limits, the right-sided limit and the left-sided limit both approach 0, then the limit does exist, and the limit is that number. It's 0. Okay? So the limit exists, and it equals 0. So I go up here, and I write my answer. It's equal to 0. Okay? Again, you could graph it, and you would note that it's that they would meet at 0. It would not be a removable discontinuity. Anybody want to see the graph for that? Yeah. Sure, real quick. So for x is less than or equal to 2, it's going to be this parabola. So that's a parabola with a vertex at 2, and it's going to be a filled in dot because it's less than or equal to 2 there, and it's going to be opening up. So a parabola looking like that. And then this portion is going to be the line negative x plus 2. So 1, 2. The y-intercept would be right here, but because that's not part of the domain of x is greater than 2, we're not going to actually graph it. We're just going to use it as reference. And we go, here's y-intercept of negative 2, then we go down 1 over 1, and we go down 1, right 1. And here's where we pick it up. It's going to be an open circle, and it's going to be the line. Like that. So this circle that was open from this portion of the graph gets filled in by the filled in dot of this graph. So it's continuous and the limit is 0. The y value is 0. Okay. Other ones? Yeah. 57. Oh yeah. Okay. 57, it says, for that function, describe the intervals on which the function is continuous. So, 57, f of x is equal to 3x squared minus x minus 2 over x minus 1. Alright, that's for x is not equal to 1. And if x equals 1, then the y value is 0. Okay. Let's see if this can be, let's see if this is a vertical asymptote or if it's just a removable discontinuity. Let's see if it's an asymptote or a pothole. Okay? And we could tell that if we could cancel it out, then it'd be a pothole. So let's see if we can factor the numerator to be something that would factor with x would divide out with x minus 1. So we have 3x and we have x. The numbers that go here have to multiply to get negative 2, but then the OI part of FOIL have to combine to get negative 1. So we'd want to put negative 1 right here and then plus 2 right there, because this would be negative 3x and then plus 2x would give me negative x. So with that, the x minus 1's divide out. So that is a removable discontinuity at x equals 1. So with that being said, let's graph it and just get a picture of what's going on. For the entire domain except for at 1, the equation is 3x plus 2. So 1, 2, and then we have a slope of 3. 1, 2, 3, go up 1 over 1. But there's a hole here because that's at x equals 1. So, and the line continues like that. So that's the line, and with the pothole. If this pothole were filled by the other portion of the piecewise function, then the entire function would be continuous. But at x, this should be 1, right? This should be a 1. At x equals 1, the y value is 0. So there's a dot down here. So, is this function continuous? It is not, because this portion of the function did not fill in the pothole. If they had said instead of 0, what would this number have to be in order to make it continuous? It'd have to be 5. 1, 2, 3, 4, 5. Okay? The value would have to be 5 in order for it to be continuous. Yeah. Okay, good. So it is continuous on negative infinity to 1, union 1 to infinity. Sweet. Real good questions. I like how we started easy and then we just up the ante. Others. Yeah. 23. Okay, the limit as x approaches 0 of 1 minus the cosine of x divided by the sine of x. This looks a lot like the rule where we had the limit as x approaches 0 of 1 minus cosine of x over x. And we said that that was equal to 0, right? Remember that back when we wrote those down for the first time? And then we also have the limit as x approaches 0 of the sine of x over x, and we said that, okay, so that one's equal to 0, this one is equal to 1. So if we could get this to match that one, that'd be really cool. Any ideas how we could do that? Yeah.
Maybe pull out like a 1 over sine,
Mm-hmm.
and then maybe you have to go minus cosine x over that.
Well, yeah, unfortunately you can't separate the sine and x. Those are like, that's just bound together. That's just a number. But here's what you could do. You could multiply by x over x. And in so doing, the numerator would be x, then 1 minus cosine of x, and the denominator I'm going to rewrite as sine of x, and then put the x over here. And that's the limit as x approaches 0. So we have this portion right here that we now have matched. And it's bound to this portion by multiplication. But that's okay, because what did we say that this portion equals? 0. So if we take anything and multiply it by 0, what's the limit going to be? 0. So here, who haven't I heard from? Alexis, Jimmy, Mason. Anyone's questions you have? Again, if your review's totally out of order, that's fine. Matters not. Others, even if you've asked for one before? Any others? All right. Well, if you do, let me know, and I'll help you out.
Maybe 55, what is the bars around the x?
55.
Does x have 2 value bars?
No, that is a step function. So we haven't looked at that much. There you go. But what that is that that's the greatest integer problem. So what it looks like on a graph is this. It's you have a and then it looks like that. Yeah. So what's the greatest integer between, so like if x is 1.2, what's the greatest integer? That'd be 2. So or yeah, so then it just goes like that, greatest integer. So but we didn't do that. So yeah. 67. Sure. 67 says g of x is equal to the natural log of 25 minus x squared. Alright, and our instructions are to find the vertical asymptotes. Find the vertical asymptotes, if any, of the graph of the function. Well, the natural log is going to have an asymptote when, so just the normal natural log function looks like this. Right, so this is the natural log of x. So that will have an asymptote at 0. So where will this have an asymptote? We need to take that and say that, I'm trying to picture what the graph would look like. X minus 5, natural log of 0. Okay. When x is 0, there's a vertical asymptote, right? For this parent function. When x is 0, there's a vertical asymptote. So when this is 0, there will be a vertical asymptote. So 25 minus x squared equals 0. When that, solve that, and whatever values you get, so whatever values would make this become 0, that's when you have a vertical asymptote for the natural log. So what would the answer be for that then? Yep. So add x squared and then take the square root of both sides and you get plus or minus 5. Yep. Others? You can work there if you want. Yeah, please. Which one, guys? 77. 77. The limit as x approaches 0 from the right of the natural log of sine of x. Okay. All right. So we need to find the one-sided limit. For this one, I'm trying to remember if there was a rule for natural logs or not that we discussed. And off the top of my head, I'm not thinking that there was. There might have been. But so if you can't remember, I would try tables. I would just try to make a table real quick to see what happens. If we were to plug in, even before that, we need to try direct substitution. Sine of 0. What's the sine of 0? 0. What's the natural log of 0? No. Does not exist, because back up here, natural log of 0, vertical asymptote. Right? So direct substitution fails. So for this one, I would try to just make a table, and make a table of values as x approaches 0 from the right. So from the right, that means numbers bigger than 0. So I'm going to try 2, 1, 0.5, 0.25, and you know, we'll see what happens there. So that's x, and then this will be f of x, or y. Okay, so let's see what happens. So I'm going to type in 2 to my calculator, and I get 2. And then I'm going to type in the equation is ln sine of x. And make sure we're in degree. Degree mode is fine. So ln times the sine of my answer. And I get negative 3.35 for 2. And then for 1, I get 4.048 negative. And then for 0.5, I get negative 4.74. 1. And for 0.25, I get negative 5.4. And 3, 5, and it doesn't look like it's increasing crazy yet. So let's try a number that's even more radically close to 0. Let's try 0.00001. So 0.00001, and plug that back up in there, and we get negative 15.56, and that's getting bigger. So let's maybe even try something bigger. That's 8 zeros. And then plug that in there, we get negative 27, 0.0000001, and it's negative 27. So from there you can tell that indeed it is getting lower and lower and lower. So what would the limit be for this one? Negative infinity. Yep. Equals negative infinity. That's what I'd do for that one.
So this would be
Yep. So if you had to do this without a calculator, tables. All right, same thing tomorrow. So come with your questions. Tomorrow. And if there are none, that's fine too. We can just work the whole period, and we'll be